Okay, welcome everybody. Thanks so much for joining me today. Close the door behind you, please, as you're coming in. My name is Brandon Minnick, and in this session, we're talking about correcting common async await mistakes, specifically in .NET 8. Now, we're gonna move fast. There's a lot of material we have to cover. Async await came out in C# 5, and now we're on C# 12, so there's been a lot of goodies added. So don't worry about trying to take notes. Don't worry about trying to keep up, because I've actually taken all the notes and given you all the things for you right here on this website. So if you get a chance, take out your camera or take a picture of this slide. You can use this QR code to go to codetraveler.io/async-await-best-practices. This is where you can find these slides. This is where you can find a recording of this talk. This is where you can find the open source code for all the demos we're gonna do today. So relax, soak it all in. Like I said, we're gonna be moving quickly. And if you do have any more questions, I'll be around all week. And you can always find me on Twitter. My handle is @thecodetraveler, so feel free to reach out if you have any more questions. Okay, well, let's start by looking at this async task method. This is a method called getLibraries. It's going to call http://client.getAsync, hit this API, return a response, ensure we got a good status code. Then we're gonna read that response, get the content, deserialize it, and return the list of libraries. Now, what's really going on here is, let's say thread 1 kicks off this method. So thread 1 comes in, thread 1 initializes this variable response, and then as soon as thread 1 hits that await keyword, it returns. And a background thread comes in this case we'll say thread 2, but it could be any free thread in the thread pool, will run http://client.getAsync. And this is good, because thread 1 is a very, very important thread. It's also known as the UI thread. It's also known as the main thread. Thread 1 is the only thread that can redraw our UI. It's the only thread that can respond to a user. When they tap a button on our app, thread 1 is responds to that button click. If they scroll on a list, it's thread 1 that's redrawing the UI. So we don't want to overuse thread 1, and we definitely don't want thread 1 making any API calls that take a couple seconds, because if thread 1 does, that essentially means our app is frozen for a couple seconds. So it's a good way to get a 1-star review, have the user force quit your app and tweet about how much they hate you on Twitter. So with the await keyword, we're running this on a background thread. Meanwhile, thread 1 is free to interact with the user, respond to the UI, button clicks, all that fun stuff. So when thread 2 is done, it calls back out to thread 1 and says, hey, thread 1, I'm all done, you're back up. So thread 1 jumps back in. Thread 1 runs response.ensure status code and initializes the variable stream. And then we hit the await keyword again. So what happens? Well, we grab another background thread, whatever thread is free in the thread pool, we'll come in and run read as stream async. And likewise with last time, when thread 5 is done here, it's gonna call back to thread 1. And thread 1's gonna jump back in again. It's gonna initialize this variable for libraries. And then we hit the await keyword again. So background thread will deserialize, give us our list of tasks. And then finally, thread 1 jumps back in for our last time to return the result. So to understand what's really going on here, it helps to look at the compiler-generated code. So I have up here on my screen, we've gone to a website called sharplab.io. If you've never heard of SharpLab, this is a really, really cool website where you can see what the compiler is actually doing with your code. In fact, it's so good that the .NET team at Microsoft actually uses this, because we can see here that it has all the different branches of the Roslyn repo, different platforms. So literally, the C# team, when they're implementing new features for us, they'll come in here to try them out. So highly recommend sharplab.io if you haven't used it before. But what we have here on the left is that same code. So this is our getLibraries method. And on the right, this is what the compiler has generated. So if you don't know, the way the compiler works, when you first click compile, it does what's called lowering. So it takes the code we write and turns it back into something that the compiler can understand. Because if you think about it, the compiler's got to support all the way back to C# 1, and when C# 1 was invented, async await didn't exist. Like heck, multi-threading, thread pools wasn't even really a thing. Even things like we get like var, that gets lowered back into the type so that it can go through the compiler in a way it understands. And what happens here with our async task method is we see that the compiler has created a private struct that inherits from IAsyncEnumerable state machine. Now, quick fun fact, we're looking at the code as if it was in compiled for release mode. When you're in debug mode, it looks a little different. It'll be a class, but when we're compiling for release, the compiler goes ahead and optimizes a little bit for us. So we get a private struct, and right away that's a little weird, right? Because I just wrote a method, but now the compiler-generated code is this struct that inherits from IAsync state machine. It's got all these funny names in it, like angle bracket, get libraries, d__2, and this, if you squint and look closely, this is the name of my method. This is my get libraries method, but what the compiler does, because it's generating this class and it doesn't want to have a naming conflict with any other classes or structs that already exist in our class, it adds these angle brackets, which is a cool way to cheat because we can't do that. Like, we can't add an angle bracket in our code. We'll get all sorts of weird errors for our class names, and the compiler knows that, so it writes some illegal code that it knows we'll never be able to write. That way, we don't have any overlap with its compiler-generated code. But let's take a look at what's going on here. So inside this method, or inside this struct, is a method called moveNext. And right away, this is something that perplexed me when I first started using Async Await. I've been making iOS and Android apps in C# using Xamarin and .NET MAUI for about 8 years now. And I'll never forget when I first published my app to the App Store, I kept seeing these weird stack traces. I'd get back these crash reports and bug reports from the app, and moveNext would be everywhere. And I was like, what is this? Because I never wrote a method called moveNext. Turns out the whole time it was just the compiler generating it for me. But what moveNext is essentially a giant state machine, or more specifically, it's a giant switch statement. And inside of this switch statement, the compiler adds a case every time we use the await keyword. So in this example, we're using the await keyword 3 times, and you can see that the compiler generated case 0, case 1, and case 2 for us. And there's also this default case here, which every time this gets generated, it'll always have at least the default case, and then every time we add the await keyword in our method, the compiler adds another case. And if we look at what's going on here, this is actually just our code. And again, it looks a little silly, like there's these angle brackets, but we see we're just calling getAsync when we first enter this. And so the first time moveNext is called, it looks at this variable called num, and num is just whatever the current state is. And the current state, the first time this runs, will always be -1. And since there is no case of -1, we jump into the default case, and that's where we call getAsync. Now, what the compiler does, or the code the compiler writes, will first look to see, did that task complete? Because sometimes we write methods that are async tasks, but we return task.completed. And it's pretty cool because the compiler is smart enough to know, hey, if that task is completed, we don't need to switch threads. We don't need to do that. It's expensive. We don't want to do it. And so the first thing it'll do will say, is that completed? Because if so, we can just move on. But we know in our example, we're calling an API. It's going to have to reach out. This is going to take a couple hundred milliseconds, if not a couple seconds. So it's not completed yet, which means we enter here where it updates the state to 0 and returns. And this return is how thread 1 is now free to return and interact with the user. But again, before it left, it set the state to 0. So as getAsync is now running on a background thread, once it finishes and it shouts back and says, hey, I'm all done, and thread 1 jumps back in, again, it sets this value of num to the current state, jumps into the switch, and now we're in state 0. So this is how thread 1 knows where to pick up where it left off. And in this case, it's a little strange because the compiler is using goto statements, and we probably don't and probably shouldn't use goto statements in our code. But all this is saying is to jump to this line, IL007E, which is down here. And in case 1, we can see our code again, where we're calling, first we're getting the result, setting that variable result to the get result value, and then ensuring we have a success status code. And then, again, just like last time, it kicks off read as stream async. And just like we expect, it first checks to see, is that already completed? If not, okay, I'm gonna go return, I'm thread 1, I'm gonna go hang out with the user so that our app doesn't freeze. And so this goes back and forth, and this is how the C# team was able to design for us async await. So like we get this pretty syntax here in our code where it just says we have this async keyword, we have this await keyword, it's very readable, we can read it top to bottom, left to right. But if you think about it, this didn't exist when C# was first created. So super, super smart people on the Microsoft runtime team were able to figure out a way to take an existing language, an existing runtime, and create this state machine for us, while us as the developers consuming it, we get to use this really cool syntax. So that's how it's working under the hood. But what I want to highlight for you is this try-catch block here. And if you look, this try-catch block consumes the entire code. So this try-catch block, again, I didn't write this. I don't have a try-catch block in my code. But this try-catch block takes all of the code from our async task method and puts it inside of a try-catch block, which means if any of my code throws an exception, it gets caught right here. It gets caught in this exception handler. And this is OK, because as long as you use the await keyword, this exception gets rethrown. But when I was first learning async and await, I thought I knew what I was doing, and I would do things like, well, I want to run this code on a background thread, so I would say task.run, I'd put a bunch of code in it, and I'm like, I don't need to await it because I don't care when it finishes. And that is actually what led to all those bugs in my first app, because what I didn't realize was sometimes my code is throwing an exception. You know, I'm a mobile developer. As mobile developers, we know we can't trust your internet connection on your phone because it's going to switch between Wi-Fi and cellular and different towers, and maybe you're on a bus and you lose your Wi-Fi altogether. So sometimes my code was failing, but it was inside a task.run that was swallowing up the exception. And because I wasn't awaiting task.run, I never saw that exception. And you might think to yourself, hey, that's great. I hate exceptions. They crash my app. I love this. But in reality, exceptions are good. We want those exceptions to be thrown because if we get a timeout exception, if we get an HTTP exception, we want to be able to handle that gracefully because different scenarios are going to pop up, and we need to be able to tell our app what to do when things fail. Whereas what was happening in my app was it was just failing, and then the rest of my code kept going as if everything was cool. So weird things were happening, and it was all because I didn't know about move next and how this worked with this try-catch block. So let's do a quick review here. The async keyword adds about 80 bytes, and that's because every time we compile our async code, that async method becomes a struct when in release, and if it's in debug mode, then that's still a class so that the debugger can better handle it. Struct is a little bit more performant, which is why it does that in release mode. And this is actually a fun improvement in .NET 8. This used to be about 96 bytes, I think, and in .NET 8, they made some optimizations, squeezed it down to 80 bytes, but we're talking 80 bytes. This really isn't much nowadays. Like, even as a mobile developer who has a limited amount of RAM to work with, I don't really care if my app size increases by 80 bytes. Probably most of you don't either, but fun fact to know about, because maybe one day you'll be working on an embedded system or an IoT device, and you don't want to increase your app size, and now we know that the async keyword increased our app size by about 80 bytes every time. And we want to await every task. And again, this is because non-awaited tasks hide exceptions. Again, it might sound like a good thing, but it's a bad thing. We want those exceptions to be rethrown. We want to be able to handle them gracefully. We want to be able to tell our app, hey, something went wrong. Maybe display to the user, error, internet connection could not be established, something like that. Whereas if we don't await the task, that exception gets swallowed up forever. Okay, so now that we're basically async await experts, let's jump into some code I have and fix it. So this is an app that I've created called Hacker News that if you've never heard of Hacker News, it's a website where you can go and find kind of the latest tech stories. And I made this app that just goes out to the Hacker News API, fetches all the top stories. So when you do a pull refresh, it gets all the top stories. And then you can tap on any of these to see or to read the story. So this is the code we're going to be fixing today. And like I said earlier, don't worry about memorizing anything, because right now we're working on this class called News View Model Bad Async Await Practices. But all the things we're going to fix are already fixed inside of good async await practices. So when you come back later, you can just compare them side by side, and you don't have to remember everything we did step by step. But we got a lot of things to refactor in here. We got a lot of things to fix. So let's jump into it. Now, this first refactor, I'm getting yelled at because I'm calling an async task method here in my constructor. And it's yelling at me because I'm not awaiting the call. And this warning isn't wrong. It says, you should use the await keyword, but it doesn't say anything about the fact that it's going to swallow up exceptions. I wish it would. Actually, I used to work at Microsoft and tried really hard to get the .NET team to add that in because I was like, people don't know about this. We need to add it in the warning. But it's also correct in saying that the execution will continue to the next line while that method's running in the background. But anyways, yeah, we're here in the constructor. We have an async task method, and I literally just said we need to await every task. So how do we do that, right? I mean, if we put await here and we add async here, we're just going to get red squiggles because the constructor can't do async await, and it shouldn't. Constructors are just there to initialize our app. It's to maybe assign a couple variables and then place all this code into memory. So constructors shouldn't be doing any async await, which is why they don't allow us to do async await. So that's nice. That means they don't allow us to kind of shoot ourselves in the foot there. But if we can't do async await here, what are our options? Well, one option is I could create another method called refresh, and then I can call this code inside of it where I can await it, and then back here in the constructor, we'll just call that method. Now, I can feel some tension in the room because I just wrote an async void method. And what does every teacher tell you? Never use async void. And that's not bad advice. My advice is actually avoid async void. But the problem I have when folks tell you never use async void is they never tell you why. So why is this bad? Why is this dangerous? Well, first things first, let's add a little bit of code here. So just to show you refresh, this is the method that runs when the user does a pull to refresh. And it's going to go get the top stories. It's going to add them to our top story collection. And so if we add some code here that says maybe top story collection dot clear and top story collection dot add, and so now we're working with the top story collection here in the constructor. But let's think about what's happening, because let's say thread 1 initializes this constructor. So thread 1 comes in, it hits this refresh method, so thread 1 comes into here, but then it hits the await keyword, so thread 1 returns. And that means thread 1 moves on to this line of code here. Meanwhile, this refresh method is still running in the background. So what we just introduced is a race condition. And these are fun because we're editing top story collection here, but meanwhile, this refresh method is also running in the background and also editing top story collection here. So by having this async void method in there, we've just introduced a weird condition, and we're going to see weird bugs on our app that'll take us forever to figure out and fix. Well, not us, because now we're experts at it. But this is bad. And so the other problem with this is, IntelliSense doesn't tell us that this is async void. If I zoom in here, and if you're like me, I rarely read the docs. I use a lot of IntelliSense, and only when I hit a problem do I ever go back and look at the docs. But if we look at the IntelliSense here, it says this is a private void method. So as C# developers, we are absolutely in the right to assume that this method is going to finish before the next line of code runs. But as an async void method, now it won't. Now we know that this method's actually still running in the background. And sure, you could argue, hey, this method's right here. Like, how can you miss it? It's always going to be right there. But what if it wasn't, right? Like, what if this async void method is in a different class, and you have somebody on your team that doesn't know it's async void, doesn't understand how async void works? Well, they're going to write this code and have that assumption that because it returns void, this method's done running once it returns. But now we know that that's not true. So that's one of the reasons async void is dangerous. Another reason is, what if this code threw an exception? The refresh method might throw an exception in itself, but we can just say throw new exception here just to really ensure that exception happens. And you might think to yourself, well, okay, yeah, no problem. Exceptions happen all the time. We were just talking about how good exceptions are, so I'll just put this in a try-catch block. No big deal, right? Well, again, let's think about what's going on. So thread 1 enters the constructor, thread 1 enters the try-catch block, enters the refresh method, hits the await keyword, and then returns. So thread 1 continues on, and thread 1 continues to the next line of code. So thread 1's now down here, and meanwhile, this task is still running in the background. So we've effectively just exited our try-catch block, and now when this exception happens, our app's going to crash. There's no way we can catch it. So this is the other reason async void's dangerous, is it's almost impossible to catch an exception if it gets thrown inside or gets thrown from an async void method. So this is bad. We don't want to do it. We want to avoid async void. So let's scrap this. But what do we do, right? Because we have this code, we want to kick it off, and for me, I want to make sure that I'm showing the latest stories as soon as the user launches the app. Because if I don't call refresh here, it's a really bad user experience to launch this app and just see a blank screen and then have to pull to refresh it yourself. Like, could you imagine launching Instagram and just seeing a sign that says pull to refresh? Why? I just opened the app, do it for me. So I really want this here, but what can we do? Because we don't want to use async void. Well, I've created an extension method for us called save, fire, and forget. Now, with save, fire, and forget, if we dig into its source code, what it's doing is essentially the same thing. It's utilizing async void, because again, this is a valid use case of async void, but there be dragons. So with save, fire, and forget, it still uses async void, but it has all the guardrails there for us. So what we do here is we have our task run inside of a try-catch block, and we allow you to pass in an exception handler so that if you want to, you can handle any exceptions that pop up. So for example, we could say trace.writeLine, pass in that exception and make sure that we still acknowledge it and still recognize it. And the thing I really like about this save, fire, and forget extension method is it's very explicit. So other developers, when they come and look at your code and other members of your team, you're being very explicit saying, hey, I'm not waiting for this method to finish. So yeah, maybe don't do this top story collection stuff here because that's going to be a race condition. So it's a safe way to do these fire and forget methods, and it's better than what I used to do, which was just task.run, forget about it, because it'll still allow us to catch the exception, handle the exception, just like we always want to. So perfect. So first one's done. Next up, we get to this refactor. Now this looks a little weird, right? Because we are creating a task. So we're saying task.delay, and we're setting it to this variable. And this is another thing we can do. We can create this task first, and then we can await it later. So in this case, this is actually a little trick that we use for mobile app development, where it sounds counterintuitive, but every time a user does a pull to refresh, we're going to make him show that activity indicator, that spinning activity indicator, for at least 2 seconds, because sometimes data gets cached, and if that API request comes back within 200 milliseconds, then that's not enough time to update the UI and show that activity indicator. And so the user's going to do a pull to refresh, and they're going to think we didn't do anything. And we're like, oh wait, it didn't happen. Something's broken, and they'll just keep pulling to refresh, and they don't know that they have the latest data, but they'll think our app's broken, and that's another good way to get a 1-star review. So again, a little weird, but something I recommend doing is having that consistency by having this minimum refresh time task. Now, I got a little squiggle here, and this one's yelling at me because I'm not passing in a cancellation token. Now, as good C# developers, we always want to, anytime we have an async task method, we always want to have a cancellation token as a parameter. So anytime we write async task method, always allow the other developers to pass in a cancellation token, because maybe I don't want this to run forever. Like, maybe it'll take 20 seconds for this to time out. Well, that's not a good user experience. I want to be able to have a cancellation token that says, yeah, try it for 5 seconds, and if it doesn't work, that's when we'll alert the user. So as good C# developers, we pass in our cancellation token, and lucky for us, task.delay has that as a parameter, so we can just pass it in here. But let's pretend like it doesn't. Let's pretend like we're using somebody else's code, and they're not good C# developers like us, and they didn't allow us to pass in a cancellation token. Like, what do we do? Well, there's a cool extension method called waitAsync, and we can pass the token into here. And what this extension method basically does is bolts on that cancellation token to this task. So if you're ever working with somebody else's code or a library, especially if it's older, they might not have or they might not have given you a parameter to pass in your cancellation token. That's okay, because we can always say .wait async, and we can pass in our own cancellation token, and it's essentially bolted that on to the task. So in this case, since task.delay allows us to pass it in right there, we'll just keep it in here. Now, the next thing to refactor, let's see. We go and retrieve the top stories. Great. So we've got to get the top stories before we can add them to our collection. This makes sense. But what do we do here? What's wrong with this, right? Like we're still calling await. This looks like good code. But again, let's remember what's going on here. And so let's say thread 1 kicks off this method because pull to refresh, that's a UI event. So it's highly likely that thread 1 will enter the method refresh and get to here, and then thread 1 returns. So great. We're doing this all on background threads. Everybody's happy. Thread 1's free to interact with the user. They can scroll. They can click on the stories, do whatever they want in my app. Great. But when it's done, this, like we saw earlier, this shouts back to the calling thread and says, hey, I'm all done. Thread 1, get back in here. And now thread 1 has to come in to finish this method. Now, is that a good use of thread 1? Not really, because we're in my view model. This is code that never touches my UI. So I know I never need thread 1 anywhere in this class, but yet we have thread 1 coming back in to do extra work. And then on top of that, what if thread 1's busy, right? Like maybe the user's scrolling, so thread 1's got to redraw the UI on the screen as they're scrolling through. Well, now we have to wait for thread 1 to be free before it can come back in. So we also run the risk of our code sitting idle along with overusing the UI thread. So what we can do is we can add configure await false to the end. And configure await false basically tells .NET, I don't care what thread we continue on. When I'm done, just grab whatever thread is free from the thread pool and keep running the code. And so now, instead of returning to thread 1 after this line of code to clear the top story collection and iterate over it to add them to the list, now .NET will just go to the thread pool and say, hey, who's free? And it'll take whatever thread's available and it'll continue on running the code. So with configure await false, we can be sure we're not overworking and overusing our UI thread, and we get a little bit of a performance bump because again, if thread 1's busy, well, we gotta wait for it to free up before we can jump back in. So my rule of thumb is, with mobile and .NET MAUI specifically, we use the MVVM architecture. So everywhere in my view models, everywhere in my service layer, everywhere in my code that doesn't touch the UI, I configure await false everything. But obviously, if you're writing UI code and you need to return to the UI thread to maybe update some button text or something like that, of course, don't use configure await false. The default is actually configure await true. So if you don't have configure await on there, it'll default to configure await true. But then also, new in .NET 8 is configure await options. We can now pass in an enum here. And this enum has a couple options. And right away, you'll see the values here on the side. So this is a flag. So we can actually chain these together. But let's talk about what they do first. So there's configure await options.none. And this is going to be a little counterintuitive because .none is the same as configure await false. So .none means don't return to the calling thread. Again, little counterintuitive. When I first saw this, I was like, oh, cool, configure await options. I assume .none's the same as true, right? Because they're both the defaults? No. configure await options.none is the same as configure await false. It will not return to the calling thread. The next one here on the list in IntelliSense is configure await options.force yielding. So this is basically the modern .NET way of saying await task.yield. So remember when we looked at that compiled code, it said every time we kicked off a task, it would immediately check and be like, hey, is this task already completed? Because I don't want to have to switch threads if I don't have to. Well, force yielding says always switch threads. And again, probably a little weird to think about, but if you've ever had to use await task.yield in your code to force a thread switch, then this is the way to do it nowadays in .NET 8. And this can be super helpful because again, if we're updating code that needs to yield, then maybe we want to update something on the screen with the UI thread, then force yielding will make sure that once this code runs, we will always make that thread switch. So there's force yielding, There's suppress throwing, and this one goes against everything I just talked about because I always said you want to rethrow those exceptions, we want to use the await keyword, but now you have the option not to. So don't ask me, I don't know when you would want to use this in your code, but you can say configure await options.suppress throwing, and if an exception is thrown in your task, .NET will not rethrow it for you. So little dangerous. I don't know where anybody's going to use that. If you do, let me know. I'd love to know a real-world example. And then the last one here is continue on captured context. So this is the same as configure await true. So continue on captured context will return to the calling thread before running the next line of code. So again, these are also, this is an enum flag, meaning we can chain them together. So we can always use that bitwise OR and say, we want to force yielding and suppress throwing by putting them in there together. So play around with those, but I will say for my code, most of it, I'm using configure await false, unless for some reason I can think of a good reason to use, use the other ones otherwise. Okay, cool. So that refactor's done. Now, what's next? Oh, great. So down here, we finally have our minimum refresh time task. So in our finally block, this is where I'm going to say, hey, if all this code, if all these API calls took less than 2 seconds, hang out here for a bit, because I want to be sure the user knows we acknowledge their pull to refresh and they update the UI, they get the activity indicator. 2 seconds is just enough time to say, hey, I acknowledge you, but not enough time for them to be angry at us for wasting their time. But the problem here is I'm calling .wait. Now, I have a rule of thumb, and that is to never, 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 never use .wait. .wait is really bad. The reason .wait's bad is unlike the await keyword that will return the calling thread, so again, when we use await, the thread's able to return either back to the thread pool, or if it's thread 1, it can interact with the user again. .wait says, calling thread, you're staying right here, and it locks the calling thread on this line of code. Meanwhile, this minimum refresh time task is already running on a different thread. So bad things are happening because this is going to wait 2 seconds, so if we are on the UI thread, that means our apps can be frozen for 2 seconds, but it's also bad because we're using 2 threads when we should only be using 1. And even if you're thinking to yourself, like, hey, I don't really care about this UI stuff, I'm a back-end developer, I make ASP.NET Core APIs, what do I care? Well, if you use .wait, even if you don't have a UI to worry about, you're still using 2 threads when you only need to be using 1, and eventually you're going to reach what's called thread pool exhaustion, because every server, every computer only has a finite amount of threads that .NET can have in the thread pool. And that all depends on how much memory and basically how much horsepower your server has. .NET will determine how many threads it can spin up. But yeah, even if you're just making APIs and you don't care about freezing a UI, well, every time you call .wait, you're using twice as many threads as you need, and you're going to hit that thread pool exhaustion twice as fast. So what do we do? Well, easy solution here because we're in an async task method, so we're just going to await it. But let's say maybe you can't, right? You know, it's getting really, really rare nowadays, especially in the .NET 8 world where you'd ever have to write synchronous code. But it does still happen, you know, probably 99% of the time we can just use the await keyword, but that 1% we might have to use .wait. And I just said, don't ever use it. Well, what do I recommend? Well, we can instead use getAwait or getResult. Now, this is still bad. This is still going to do everything .wait does. It's still going to lock the calling thread. We're still using 2 threads when we should only be using 1. But if an exception is thrown, so let's say that our cancellation token timed out, and this is going to throw an exception, a timeout exception, well, getAwait or getResult throws our code. It throws that timeout exception. Whereas if we're using .wait or .result, that throws what's called a system.aggregate exception. And if you're unfamiliar with those, they're really weird because an aggregate exception is an exception that holds exceptions. So it has a list of exceptions inside of it. And that's where our code lives. So if you've ever seen those stack traces, system aggregate exceptions are weird. They're difficult to debug, especially for new developers, because you're looking at it and you're going, okay, I don't even see my code that threw an exception. I have no idea what this aggregate exception even means. Whereas if you use getAwait or getResult, it'll rethrow our code with our exception in that stack trace. So it's still bad. We still don't want to use it if we can just use async await instead. But if we have to, get await or get result is better than .wait and .result. It actually replaces both of them because it'll rethrow our code with our exception. OK, but for here, we're not going to do any of that. That is more of a fun fact than anything else because we're in the async task method and we'll just await it. And also fun fact, yes, you can use async await in your try finally blocks. OK, next up, we've got this method called getTopStories. Now, this looks pretty good. Another cool fun fact here, we're using a frozen set. This is something new also in .NET 8. It has nothing to do with async await, but I love it because I'm a big fan of immutable data. I strongly believe anytime we make an API call, anytime we pull data from a database, that we should store that in an immutable list. And that's what frozen set is. You can see it's in the namespace system.collections.frozen. So new in .NET 8 is frozen set and frozen dictionary. And some of you might be thinking to yourself, like, hey, wait a minute. I've already used things like IReadOnly list and immutable array and immutable collection. Like, why did they go create a third one? What the heck's the difference? Well, the frozen set is the only one that'll actually freeze the data. Yes, if you're using IReadOnly list or immutable list or immutable collection or any of those existing ones, yes, you aren't able to add or remove anything from the list, but a savvy developer might know you can actually go into and replace the data in there. So I could go back to index 0 of my IReadOnly list and I could swap out that data. Frozen set doesn't allow you to do that. So we finally have a purely immutable collection that we can use in .NET. And I'm a big fan because, like I said, I always use immutable data structures like this anytime I make API calls and anytime I make database calls. And the way you can use it is you just say .toFrozenSet. So super easy and super convenient. Now, looking at this code actually looks really good, but it's telling me I got to refactor it. So what's wrong here? Because we're using the await keyword, we're calling configure await false. But if we look at this, it's kind of a product of how the Hacker News API works, because the Hacker News API requires me to call and get the top story IDs before I can actually get the top stories. So whoever designed the API, I wish they would have just allowed me to get all the top stories in one API call, but nope, the way they do it is they got to give me a list of IDs, and then serially, I have to make a request to get every story in the list. So if I want to get 50 of the top stories, well, I make this first API call, and then I got to make 50 more. And because it's in a for each loop, this is all happening serially. So I got to wait for that first one to get back, then I make the next one. And so even if they take half a second, if I'm making 50 API requests, that's still like 25 seconds. So we can do better. And we can use something, and instead of rewriting this, I'll jump over to the good async await best practices to show you. We can use something called IAsyncEnumerable. Now, IAsyncEnumerable is really, really cool. It is an async method, but it allows us to return the results in real time. So let's check out this code real quick, because it's this IAsyncEnumerable that allows us to consume it as an await for each loop. So await for each is this really, really cool feature where if we have an IAsyncEnumerable, we can say await for each for every story in our getTopStories. And it's, again, we can just use configure await false here. We pass our cancellation token, so everything's still looking good. But as soon as one of those API calls come back, I can add it into my collection. So instead of forcing the user to sit there just looking at a spinning indicator for 25 seconds and bam, all that data shows up at once, with this await for each loop, I can feed them the data as it comes back. And we'll see in a second, I'm doing it all in parallel. So the way I've designed this IAsyncEnumerable is, I still got to go get those top story IDs, but once I have them, instead of awaiting each API call to get that story, I've created a list of tasks. And so what I do, I add all those tasks to this list, and then I jump into this while loop where I say, as long as that task is not empty, or as long as that list is not empty, and as long as the maximum story count hasn't been reached, because maybe the user only wants 20 stories, and that's fine, they can set that, keep going. So what we can do is we can say await task.whenAny, and what this does, we pass in a list of tasks here, and task.whenAny anytime one of those tasks is completed, we'll give it to us. So as soon as one of these 50 tasks is done, it returns it here, and now I have it. So I want to remove it from the list because I know I don't need it anymore in that list. And then I can get the story from that task, and I can yield return it. And yield return that's the same as an IAsyncEnumerable yield return. And if you've never used it, it doesn't actually escape the method. It doesn't return the method. Instead, it returns that one piece of data, and it's this yield return. If we jump back up to the for each loop, it's that yield return that allows us to run this code and subsequently show this data to our user on the UI. So we're able to basically stream the data to our user as it's coming in, and at the same time, we're running all of these in parallel instead of running them sequentially. So our app's going to load a lot faster, and it's a better UI experience. And I do want to point out one thing here is I just said that whenever a task completes, that's what we get back. So technically, this task is completed, but I'm still awaiting it. So there is the one valid use case for using .result, even though I just told you never to use it. We can use .result here because we know this task is completed. We know that this won't lock any threads because there's going to be no thread switching. So .result is valid here, but I still don't recommend using it because this code will get refactored someday. We're going to have new developers on our team. They're going to copy paste our existing code into their code. And I guarantee you this line of code will appear somewhere else in your app one day. And if we say .result here, and then somebody else copy pastes it, and all of a sudden now our app's freezing, performance is bad, because they didn't understand that the task was already completed. So it definitely feels like overkill to say await and configure await false, but we know those are the best practices, so we still want to do it, even though we know that task is completed. Okay. Next method, we have a method called getStory now. So this looks pretty good. We're using async await. I could probably add in configure await false here, but there's actually a better optimization here because this getStory method, if we zoom in a little bit, this getStory method returns a task of type story model. And if we look at this method, it also returns a type of task story model. So what we can do is we can remove async and remove await and just return that task. And what this does is it saves us a thread switch. So again, if you think about what's going on here, let's say thread 5 calls this method. Thread 5 comes in here, hits the await statement, returns back to the thread pool. This is now running on a different background thread, maybe thread 7. Then when thread 7's done, it says, hey, thread 5, I'm all back, or I'm all done. Or even if we had configure await false in here, it would still have to go back to the thread pool and get a different thread just to return the value. So we had 2 thread switches when we don't need to. And if we remove async and we remove await, now we just return the task, we save those context switches, and now whoever's calling the getStory method, they can decide how they want to use it. So that's why up here, you can still say await, you can still say configure await false, and we've just improved our performance a little bit by saving ourselves a context switch. Okay, one more method down here. This one's called getTopStoryIDs, and let's actually remove this for just a second, because right now we're looking at the same thing, right? This is just like the last method. It's a async task method, and the only place where we have the await keyword is in the return statement. So that's easy, right, Brandon? You just told us we remove await, we remove async, and there we go. Like, this is going to compile, there's no red squiggles. But no, this is actually a trick question, because when we return, we exit the method. So as soon as we hit that return statement, we're given back the task, which means we've exited this method, which means we've exited this try-catch block. So we're no longer inside this try-catch block as soon as we return the task. So what's happening is this method is still running on a background thread, but if it throws an exception, we're never going to catch it here. So this was actually a trick question. We do want to keep async await here, even though the only place we're doing it is in the return await statement, just because we're inside a try-catch block. Now, adding in that previous code back, something else I want to show you is, let's say, wouldn't it be smart is every time they did a pull to refresh, we check to see, is the data still good? Like, Hacker News doesn't update every second, every minute. So I kind of said, hey, if the data's recent, like within the previous hour, let's just skip that API call. Let's save ourselves a round trip. We don't need to burn through the cellular data for the user. And we'll just return what we already got. Like, we already got the IDs, just give them back. And so what happens now is, the first time we run this method, we won't have any data. So this will be false, and we'll have to do return await, which is totally fine. And we should be good in adding configure await false here. But the second time this runs, assuming that pull to refresh happens within an hour, this part of the method runs. And the third time this code runs, we use this return statement, the fourth time. And what you start to see is the hot path for the method is right here. And the hot path does not use the await keyword. So if you ever have a method like this, where 9 times out of 10, you don't need that await keyword, instead of returning a task, we can return a value task. Now, value task is similar to task. It's not exactly the same. Like, for example, you shouldn't pass around tasks, or you shouldn't pass around value tasks, and you shouldn't reuse value tasks. But certainly safe to use it as a return for a method that you can await. And the reason it's a little bit better is value task is a value type. So if you remember, in C# and .NET, value types live on the stack in memory, whereas reference types, which a task is, live on the heap. And so if we're not going to use the task and we're not going to need all that overhead, well, we can get a performance boost by using value task, because adding something to a stack, O of 1, we just push it right onto the stack, whereas anytime we add something to the heap, well, we've got to index it. It takes a little bit longer. So if we're not going to use async await, and we're not going to need the await keyword in our method, say 90% of the time, we can get a little bit of a performance bump by using value task. Okay, so let's talk about all those async await best practices. Never use .wait or .result. If you can avoid it, avoid it. It's really bad. It locks the calling thread. You're going to end up using 2 threads when you only should be using 1. And we should always be using the await keyword. But if for some reason you have to, like I see it still like old interfaces, maybe it's an interface that returns a type bool instead of a task of type bool, then okay, fine. What we'll do instead is get await or get result. Get await or get result, again, replaces .wait and it replaces .result. But it's also bad because it's going to lock the calling thread, and you're going to end up using 2 threads when you only should be using 1. It just gives you better stack traces, better exception handling, and helps out future you when you're debugging code. Fire and forget tasks. Don't do what I used to do and just say task.run, run this in the background, forget about it, because we always want to await every task. So if we do want to fire and forget a task and we know this is totally cool, we can run it in the background, I'm fine with the code continuing to run after this, use the safe fire and forget extension method. I have it available in my NuGet package, Async Await Best Practices. I highly recommend it. And I know I'm a little biased because I made this library, but we just reached over 1.5 million downloads. So a couple 100,000 developers also think it's pretty cool too. And I actually saw Mozilla's using it in one of their C# apps, which is crazy, mind-blowing. So NuGet Async Await Best Practices will give you the safe fire and forget extension method. Avoid return await. So if the only place in your method you're using the await keyword is in the return statement, you can remove it. You can remove async and just return the task. But keep in mind, if you're inside of a try-catch block, keep it. Keep return await, because you're going to exit that try-catch block right away. Likewise, if you're in a disposing, like a using block, and you're going to dispose of something, again, keep that return await, because you're going to exit the method, and then objects are going to be disposed that you're probably using in the background, and then you're going to get weird object dispose exceptions. It's happened to me. I'm telling you this from experience. Keep it in those scenarios, but otherwise, totally cool to remove it. Configure await false. So if you don't need to return to the calling thread, configure await false. Like I said, I use it everywhere in the view model layer, the service layer of my app, because it gives us a little bit of a performance bump when we know we don't need to return to the calling thread. Now, caveat, configure await false uses something called the synchronization context, and almost every framework in .NET has a synchronization context, but the odd one out, ASP.NET Core. So if you're using WPF, if you're using WinForms, if you're using Blazor, Xamarin, .NET MAUI, whatever, they all have synchronization context. So configure await false will make sure you don't return to the calling thread. When ASP.NET Core was created, they made the decision not to include a synchronization context, which if you don't know what a synchronization context is, that's cool. I've got a link to it on the webpage. It's basically what allows .NET to return back to the UI thread for us. But definitely check out those blog posts if you want to get real deep into it, because there's synchronization context and execution context. This all goes way deeper than even what we're touching on today. But right, so in ASP.NET Core, there is no synchronization context. So that means if you write configure await false in ASP.NET Core, it's the same thing as writing configure await true. So slight caveat there, but for all the other .NET frameworks, it's good. Now, there's also a configure await option. So again, new in .NET 8, we can use this enum. It's a flag. We can chain them together. And just keep in mind, the weird caveat with .none is the same as configure await false, meaning it will not return to the calling thread. It's going to be a little weird to get used to that, but by the time .NET 15 rolls around, we'll be masters. We'll know these like the back of our hand. But the other options are to continue on the captured context. We can also say force yielding, which will force the thread switch even if the task is completed. And then there's also suppress throwing, which terrifies me and would love to know why and when anybody would want to use it. And again, same caveat, it still requires a synchronization context. And so ASP.NET Core, you're the odd man out because you don't have one. Utilize value task. So when your method's hot path doesn't call await, you can return a value task instead of a task. Get that performance boost, because now, again, you're pushing that to the stack instead of allocating it on the heap, and your code's just going to run that much faster. And you'll notice a lot of things under the hood in .NET now use value task instead of task as well. So we can be just as smart as those guys using value task in our code. IAsyncEnumerable, if you're streaming data, we want to be able to show that to the user. We want to be able to stream that in real time. IAsyncEnumerable allows us to do that. So instead of telling the user to wait and just showing them a little spinning indicator saying loading, 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 we can actually give them what they're looking for. We can run our API calls in parallel, and it's a better user experience for all of us. And don't forget, I forgot actually, I didn't even tell you about enumerator cancellation. Let's jump back to the code real quick. So what is this? So we're good C# developers, so we're always going to provide a cancellation token for our async methods. And when you do that for an IAsyncEnumerable, it'll yell at you. It'll say, hey, you need to add this, or you should add this enumerator cancellation attribute. And what this does, this tells .NET that this is the token to pass into the .NET AsyncEnumerable under the hood. And the reason this is really cool, if we didn't have this in here, we would have to check that token, right? Like we would have to say things like token.throw, and we'd probably want to do it down here, and we have to make all these checks because if the token's canceled, we should abort. But with enumerator cancellation attribute, we don't have to do that because we're essentially telling .NET like, hey, every time you iterate, just check the token for me. So not too difficult to remember, because again, if you forget it, you'll get a little warning message. It'll say, don't forget that attribute. Okay, wait async. So again, if we ever have to consume an async task method that doesn't allow us to pass in a cancellation token, shame on them, shame on that developer who wrote it, but that's cool. We can just use the wait async extension method and pass in our cancellation token there, and then it's basically the same thing. It's as if they did allow us to pass in a cancellation token to their task. All right, and we also didn't get a chance to talk about IAsync disposable, so we can show it off here. It's just like IDisposable, but you can await it. So this is really cool for certain things that take a long time to clean up. If you've never used IDisposable or IAsync disposable, it's basically a way for the creator of a class to clean up after itself. So you might have some managed and unmanaged resources you need to get rid of when you know that the user consuming your class is done, like file stream, for example. It has a bunch of buffers and it does a bunch of system I/O. And so when it disposes of all those things, it takes a while, and we don't want to lock the calling thread. So they now added IAsync disposable to things like file stream. And the way this works, it's very similar to the using block we're used to, but instead we say await using, and then again, we can use configure await false right here. And so what happens is our code runs here in the middle. So inside the curly brackets, just like with a normal disposing block, our code runs. And then once it's done, once we get to that end closing squiggle curly bracket, that's when that await executes. So that's when you'll see that configure await false actually happen. Whew, OK. Well, now's your chance. If you haven't already, take out your phones, grab a picture of this slide, head to codetraveler.io/async await best practices, because this is where you can find everything we covered today. This is where I've posted a video of this exact talk. So if you have any friends or coworkers who couldn't make it today, you can send them this link and they can watch the video. They can become async await experts just like us. And like I mentioned a minute ago, this is also where you can find the resources. So you can find links to the async await best practices NuGet package, so you can use save, fire, and forget. There's links to the open source demo that we did here today, so you can compare good and bad, good view model, bad view model side by side to remember everything we touched on. And like I said earlier, this goes really deep. This feels like an advanced topic that we just covered today. We're still way up here at the tip of the iceberg. So there's more things you can learn about how value task works, about what's a synchronization context, what's an execution context, how all this stuff work under the hood. I've included a bunch of blog posts there that were helpful for me when I was learning and first starting on my async await journey, and I know they'll be helpful for you too. Thank you.